Hi, my name is Manish Gupta, and in this video, I'm going to talk about DeepXML, which is a very important XC framework, and then also talk about Astec, which is basically a DeepXML algorithm. Okay, so let's get started. Okay, I'll start with some challenges for deep extreme classification, especially for short text inputs. Okay, so when I mean deep, I actually mean extreme classification using neural networks. Okay. So, and this is a very important problem because it has several applications, right? So essentially given a query, you want to figure out different bit phrases for advertisements, right? Given a document title, you want to figure out Wikipedia categories that can be linked, that can be associated with these or tagged onto these Wikipedia documents. Given a product, you want to figure out co-bought products, or given, let's say, a user's browsing history and the web page titles of the user's browsing history, which is again short text input. You want to figure out personalized ads that you can potentially show to this user. Okay, so short text inputs in extreme classification are quite common and applicable in several scenarios. Okay. Now there are multiple challenges when you're dealing with short text, first of all, right? So basically you have very short text, so you have to make prediction using just 3 to 10 words. That's basically one of the problems. The second problem is that when you have short text, by definition, you have less number of words, and therefore fewer occurrences of these words leads to scarcity of training data. Overall number of tokens in your training data are too small. Okay, those are the two problems. Now, there are challenges associated with using neural networks for extreme classification. So, training and fine-tuning neural network with millions and sometimes billions of parameters and millions of labels can be very expensive, right? So millions of labels, right? That is what the extreme classification problem is. It can be computationally very expensive. And specifically, if I talk about short text inputs, due to scarcity of data, the accuracy may be poor also. Okay. And the third important problem that is their efficiency problem for training extreme classification neural networks is that forward prediction pass or even the gradient backpropagation pass can be infeasible when you have very large number of labels because the classification cost at the last layer is basically linear in terms of number of labels, right? So remember last layer, let's say you have some very deep neural network, some deep neural network. The last layer output that you get, now you have to basically connect it with this large output layer, right? Which is of the size capital L, very large, millions of labels. And this weight matrix W is super difficult to backpropagate through, okay? Because even if this is basically 1,000 size layer and L is basically a million size layer, that basically leads to a billion parameters in that layer, causing difficulty in training that. Now, how do you handle this? Both at the training time and as well as at the inference time. So there's a cute idea to handle this. Okay. While backpropagating, for example, from this previous layer to the last output layer, maybe you can only take a few of those labels rather than taking all of those labels. So remember, this matrix is basically this matrix W. If I consider this output size as O, right, and the large label size is L, so you have like O cross L size matrix W. Now, all of those labels are not relevant, right? Of course, in the training data, positive labels are going to be very small, let's say in the order of log of L, right? So what you could do at training time also, you could probably just sample only a few negative labels. So of course, you take positive labels and you sample a few negative labels and backpropagate only for those weights. Okay. So basically, if you have this matrix W, of course, you have to care about the entire output. But from a label perspective, maybe you can only take a few positive columns and a few negative columns. That's it. Not all the columns, because all the columns are too many. So take only a few positive, few negative columns, only update those weights. At inference time also you do the same. Basically, you are going to infer only for a few labels, few candidate labels. Of course, some of them are going to be positive, some of them are going to be negatives. You have to basically somehow get a set of good labels though, right? So, and that basically can be done using some index. So what you could do is basically, you could have, let's say, the output that is generated. And remember, at inference time, for example, imagine if you had the entire W matrix at inference time, right? So which ones would you basically choose? And you don't want to basically compute all of that dot product, this large dot product of O cross W. You don't want to do that. So which columns in W would you choose? Of course, those which lead to larger dot product values, larger similarities, right? So that's that. And how do you do that? Well, you have a vector called O, you have column vectors in W, you could index these column vectors in W into some index, right? Use face index or any of those approximate nearest neighbor search indexes, and essentially you can just do a quick lookup and then compute the actual dot product only for those column vectors in W, which are very similar, and then figure out which ones are positives and which ones are negatives based on some threshold that you're going to learn as part of these last neurons. Okay. So that's that. So the only problem, so inference time is clean, no problem. Okay, but train time is a problem. So what is the problem at train time? Well, the problem at train time is that when you're choosing a few to do this backpropagation, right, you have to depend on an index. And the index is basically based on W's. Now W's are being learned during training. So W's are not fixed, unfortunately, during training. So these future representations change for every mini batch update. And therefore, unfortunately, you can't be frequently updating the index. That's just going to take forever to frequently update this index, which indexes column vectors of W. Okay, so that's the problem. Now, to solve this problem in a very seamless manner or a more principled manner, people came up with this pipeline called as DeepXML in 2021. So we are still like 2 years back in time, but they came up with this nice pipeline called DeepXML. And DeepXML is the basis of several algorithms that have been proposed in this paper, Astec, and then in the future papers like decaf, Galaxy, and Eclair. Okay. So now to ground this discussion a little bit, let's take up some notation. So let's call L as the set of labels, V is the vocabulary size. Because we're dealing with text, we need to care about vocabulary size. Okay. N is the overall number of training points. We'll call those training points as xi, yi. And yi can be -1 or +1. So -1 basically means not relevant, +1 means relevant label. That's it. Okay. Now we're going to learn some feature representation for every for every text. For every text, you're going to learn some feature representation. So when you have these xi inputs, basically you need to get some feature representation. Let's call those feature representations as z. Okay. And then, I mean, the broad idea is that this large neural network is going to learn these feature representations Z, and then you're going to basically just multiply it with W so as to finally get a classification in your label space. Okay, so W is the final XE classifier weight. So W are these XE classifier weights, and you're basically going to say that, hey, you're going to minimize this loss. What is the loss? Well, I mean, whatever the loss you define, right? I mean, binary cross entropy loss if you're using sigmoid activations, or categorical cross entropy loss if you're using softmax activations and so on. Okay, so you want to minimize the loss over all the training points N and over all the labels L. Remember, these label set L contains positive labels, negative labels, all of them. Okay, and that's what we were thinking about. That ideally we would want to do this, but practically we can't do this because this would really require N into L, complexity of complexity of N into L kind of computations per gradient update or per inference. Okay. So you're not going to do that. So what are we going to do? So we are going to basically somehow figure out a shortlist up to 500 is what they use in the paper, but a shortlist of labels, a small set of labels. Remember, this is a shortlist of labels. Okay. So we are going to we're going to compute a shortlist of a shortlist, right? Such that we are a shortlist of labels now, such that we are not going to compute this loss over all the labels, but only going to compute the loss for every instance I. We're going to compute the loss over positive labels and the shortlist N of negative labels. Okay. So now how do you obtain this short list of negative labels will become clearer in the video. I'm going to go into deep details, but that's what you're going to do. You're going to approximate this ideal thing with this practical thing. So that's ideal, the L, and this L hat is practical, where you're going to basically approximate the computation over all negative labels with a short list of Ni hat selected negative labels. Okay. So that's that. So don't get confused. I know, although N is basically used for the total number of training points, but Ni hat is not about negative training point. It doesn't make any sense, right? Negative labels. Okay, so that's that. Okay. So now this DeepXML pipeline has actually 4 different modules to be able to get this thing done. The first module is going to train a feature representation. Now, remember what was the problem on the previous slide? As I mentioned, the problem on the previous slide was that these feature representations and things may change in the index, and somehow we want to keep the index fixed. Okay, so how is this index fixed in the DeepXML pipeline is what we're going to understand in this slide. Okay, and the next few slides. OK, so in module 1, what do? You basically compute a basic feature representation. This feature representation is not Z, it's Z0. It's a slightly different feature representation, but still very much matching. OK, so and this feature representation is actually learned using some separate task also. So it's not going to be learned on the extreme classification task, very large multi-class classification. No. OK, we're going to learn it on a simpler task. So we'll call it the feature representation that you learn using this as Z0. We'll see more details later. OK, so don't worry. But we are going to have another task, surrogate task. And based on that, we're going to learn a feature representation Z0. Think about Z0 as an intermediate near final feature representation. So we're going to finalize it at Z in a later time point, right? Basically, we'll make it Z in module 3. But you start with the intermediate near final feature representation. In module 2, you're basically going to use this kind of feature representation with an index. So you basically create an index. In module 2, first you create an index, OK, on the fixed intermediate features. So these intermediate feature representations that you learn, you create an index, and then you're going to shortlist hardest negative labels. Now, you might be thinking, hey, we thought we would create an index on W. Why the hell are you creating an index on feature representations? Trust me, it will become clearer over time. OK. But you create a feature representation using intermediate features. You create an index using intermediate feature representations that you learned in module 1, and you index them. OK, and then basically using these feature representations that you have learned using data points. I agree these feature representations are on data points, but what you're going to do is to sample for every data point. You're going to sample NI hat, the shortlist of negative labels that you're going to care for. OK. Now, and details again, we'll talk about in the later part of the video. In module 3, what do? You basically take your Z0 and somehow create Z from it. OK, so you're going to do some sort of transfer learning. OK, and we'll see how you do that again in more detail. OK, then in module 4, what are you going to do? You're basically going to take this Z and take this W that you want, right? And you're going to train for them. Of course, basically you have to train, right? Train the entire XE end to end. So that's what you're going to do. You're going to take your Z, you're going to take your W, and you're basically going to train them end to end. Of course, you basically start with your trained Z0, and essentially you do transfer learning to Z, but then Z needs to be updated. There could be some free parameters that you want to train in Z as well, besides Z0, and you're going to basically train them along with W jointly in module 4. OK. Now, in all of these 4 modules, there are several choices that one can make. First, what is the feature architecture? How do you basically get this Z or Z0? By the way, Z and Z0 follow the same feature architecture. So how do you get that, right? For example, it could be a BERT model, it could be a Roberta model. For images, it could be some ResNet model and so on. OK, so what is the feature architecture? Then what is the surrogate task? So remember, we used the surrogate task in module 1 to train it. I mean, so what is the surrogate task? What is this index which you're using to basically index these intermediate feature representations? What is the negative sampling procedure? So you get these hardest negatives. How do you get them from the index? And then lastly, how do you do the transfer? So, what kind of transfer do you do in module 3? And then clearly in module 4, you're using some extreme classifier W. What is the extreme classifier that you use? OK, so all of those are choices. And based on those choices, basically people have come up with several kinds of algorithms, Astec, decaf, Galaxy, and Eclair, which I'll cover in the next few videos. OK, now let's get into a little more detail. How is this algorithm called Astec trained? OK, now Astec, just for the sake of people who care about full forms, stands for Accelerated Short Text Extreme Classifier. For a change, they call it extreme classifier as EC rather than XE. OK, but anyway, that's that. Now, Astec follows the DeepXML pipeline. Therefore, it will have 4 modules, M1, M2, M3, and M4. OK, so we will basically talk about how M1, M2 are done in this slide, and then M3, M4 on the next slide. OK, so let's talk about M1 first. So remember, Astec is for text, short text. So essentially, you start with text. You basically have XI being represented as TF-IDF vectors. You basically, it could be large documents also, but in our case, it's basically very short text, 3 to 10 words, remember? So it's like small bag of word representation. Now, you basically get embeddings for this bag of word representation. And the way you learn a single embedding out of it is basically you take these XTs, which are, frequencies of words or TF-IDF, and you multiply by ET, which is the learnable embedding vector. OK, so you have a ET per vocabulary word. So vocabulary token, for every vocabulary token, you have an ET, and then you essentially compute a vector V as a sum over all of those vocabulary words which are present in your current document, okay, in your current instance. Okay. Now, so here this ET is basically initialized using fast text, but you can basically learn it over iterations. Okay. The other thing that you have to learn as part of module 1 is so remember now at the end of module of this particular bullet point, what you have is that you've converted a vocabulary sized vector into a d-dimensional embedding, right? D-dimensional embedding. Okay. In some ways, back of words embedding using fast text embedding. That's that. Okay. Now you learn a very simple d cross d matrix. That's it. So you've not done anything complex. You have just learned a d cross d matrix called R0 and then do a ReLU around it, and you get delta V. Okay. So you basically just for the sake of it, you started with xi. You basically got a much smaller et. So remember, this was v sized xi. This is basically d sized, and then you have done this using fast text embeddings, and then you basically have your R0, which is what you use so as to essentially get your delta V. So this is your V, and that is your delta V. So what do you do next? Next, basically, you take this and you take this and you combine. You do a residual connection in that senses, and you get the output. So you do V plus delta V. So this is V plus delta V. OK, that's that. OK, that gives you x naught hat, right? I mean, so that's basically V plus delta V. Now, remember, this is basically an interesting V plus delta V. What do you do with that? So you get a d-sized representation. Again, a d-sized representation. OK, so you use this so as to basically train a W hat on top of it. That's basically that, right? To train some extreme, some surrogate task. Now, what surrogate task is the question? Okay. So in Astec, the module 1 basically uses label clustering as a surrogate task. So what do? You have your original data xi, yi, right? And remember, yi was basically in the label space of capital L, which is millions of labels. So what you do is to basically use, if you now remember the parable video, you basically use the balanced k-means where k is set to 2. So balanced 2 means to basically get 2 raised to 16 clusters. Okay, you do like partitioning in the label space. If you remember parable, you start from the root node where you have all the labels, you divide into 2 parts, left, right, and you keep going until you have 2 raised to 16 clusters. So this 2 raised to 16 is your new label space. OK, so the surrogate task is basically classification in this 2 raised to 16 cluster space, so to say. OK, so now, and again, how is this 2 means clustering done? Well, the way it is done is basically for all the data points, you essentially take you essentially take xi and you come up with label representations like that. So basically, if you have a label L, OK, if you have a label L, you take all of those points where label L is relevant. You take their averaged representation. OK, so remember, xi was a representation, bag of words representation. You take the average representation that gives you a representation for the label, and that's the label representation that you use. I mean, of course, you essentially take the unit vector in that direction, just like you do in parable in that sense, right? And then you do balance 2 means clustering so as to get 2 raised to 16 clusters. And module 1 literally does this. Module 1 essentially learns your W hats, and of course, it also learns your R naught and also learns your E, right? So there are 3 things that are being learned, W hat and Z0, where Z0 basically comprises of E and R naught, right? So you learn those so as to essentially minimize the classification loss in the surrogate task, right? So that's basically that. Now what is W naught? W hat? You see W hat is D into L hat. It's not the entire label space millions. No, it's not millions. It's just 2 raised to 16. That's it. Okay. So that's that. Basically, that's that. Now 2 raised to 16, by the way, is not very large. It's not millions basically. Okay. So now once you're done, so why were we doing all of this? OK, so remember, we are doing all of this just to basically get a very good representation V. OK, very good representation V, and also get a very good representation X naught. OK, in fact, after you're done with all of this, you're basically going to throw away W hat and R naught. W hat and R naught are not useful. So you're basically just going to retain this V guy here. All of this just to learn these awesome embeddings ET, by the way. OK. So what are you going to do in the first module? When it's done, you basically throw away W hat, throw away R naught, basically after the training is done. What is module 2? In module 2, remember, you had to basically index things. So basically you index these V's. You basically index these V's. You use V's to sample hard negatives. OK. Remember, in module 2, what do you need to do? You need to sample hard negatives. You have a basically label, and you basically, for any xi, you have like positive label and you want to get negative label set, right? A short list of negative labels, up to 500 negative labels. Now, how do you get that? Okay. So let's see. So you basically get that by creating two indexes, an approximate nearest neighbor search index X and an approximate nearest neighbor search index mu. There are two indexes that you use, by the way. Okay. So in ANNS X, you basically index VIs. So remember these VIs. So you obtained VI per document. So that's what you index there. And in ANNS mu, you basically index mu-L. Basically, mu-L is just the bag of words representation. So good to notice, mu-L is a syntactic representation, VI is a semantic representation. Remember that. Okay. So that's how you get these two indexes. And then when you want to sample negative labels, the way you do that for any data point, xi, how do you sample negative labels? Well, you basically ask both the indexes and you take the intersection between them and take 500, top 500. Okay. So how are you going to do this? So you're basically going to take those particular labels. You're going to take those J's from this index. So this one basically looks up using VI. So you basically have a data point, you have the VI, you find other VIs which are very similar. So you take those J's, okay? So, and then you will basically take all of those labels. So when you sample, what do you get? You basically get other data points which are J's, right? So you're basically then going to take all of those labels such that YJL is 1, but YIL is -1. Okay. So what kind of labels are you going to take? YIL should be -1. Remember, you want to sample negatives for a data point xi. So your data point xi, you're going to take those labels such that they're negative for I, but they should be positive for j's which are very similar to I. Okay, so that's the point. Okay, and the similar thing you're basically going to do in the mu space. So you're basically going to take, you're going to find those representations. So you're going to basically, so mu's, by the way, are in the label space. Mu's are in the label space. Okay. So essentially, therefore, you're going to find all of those other labels which are very similar. And then you're basically, of course, going to take only those labels which are very similar to VI. You basically take the VI, you search on the on this labels on this ANS index mu with that, and you're going to take those labels which are negative. So you want to, of course, make sure that you are taking negative labels for I. Okay, so that's how you sample in module 2. Now module 3 is super simple. So module 3, what do? You basically get final feature representations. Now these final feature representations, remember this is the transfer learning step. So here you transfer the V guy. So you take the V guy and you transfer it. So just like in module 1, you are training, you're training for the surrogate task. Here you're going to train for the actual task. The way you're going to do that is as follows. You take the X, you're going to use your embedding E from module 1, train from module 1, so as to basically get your V's. And then just like you were getting them here, right? And then once you get your V, you're basically going to learn a new matrix R, which is D cross D, so as to basically get a representation delta V this time, this delta V guy. And then you're going to basically take your V and take your delta V. You're going to take both of them, right? And then you're basically going to pass this guy to the entire label space. Okay. This matrix that you learn is basically going to be your actual W. Okay. Now notice what is the transfer learning that you have done? You transfer learned E from the previous from module 1. So that is in some ways you transfer learned V. Okay, but you computed your own delta V by basically bringing in your new matrix R. Okay. So if you look at the neural network architecture, it's actually a very simple neural network architecture. I mean, it just involves some dense layers. That's it, by the way, right? Now, to make sure that the R and R naught are not very different, you basically restrict their spectral norms to a value lambda less than equal to 1. Now, of course, some of you may not know what a spectral norm, so look into the paper to figure out how a spectral norm of a matrix is computed. It's related with the eigenvalues and so on. Okay. So it's just a norm of a matrix, basically, right? No big deal. So that's how so you want to also make sure that R and R naught are not very far away from each other, because they're far away from each other. The negatives that you sampled in the module 2 will not be valid for module 3. So as to make sure that they're valid, you want R and R naught to be very close to each other. Okay. So what does this do? This basically makes sure that your index is created only once. It's a very beautiful trick, right? So one index basically is in the feature space, the other index is in the label space, and you basically ensure that your that your indexes which were created in the label space are just created using syntax, using syntactic words. So no weights are involved, right? So therefore, index needs to be created only once, and then index can be actually used and updated. So in module 3, so the index is not updated, but essentially the weights can be updated making use of the same index vectors. Okay. So that's that. Now in module 4, of course, module 3 basically just sets it up, but the actual learning happens in module 4, where you are going to essentially use the shortlisted labels and all the training points so as to essentially learn both W and you're going to learn both W and also you're going to learn your transformation matrix R, your transformation matrix R. So that's that. That's it. So basically now once this, so this is the 4-step procedure as Astec would do. Now Astec actually adds another procedure called as re-ranking. Now it turns out that you consider hard negatives and that's great, but remember that was based on the transfer. So therefore your hard negatives may not be really good negatives. Therefore, what you do as after your Astec training is finished, you do one more round of training. And this time you basically do using yet more negative labels. And how to get those negative labels? Now this is more like active learning in some ways, very broadly. But the way you do that is as follows. You take your trained Astec model, you take your training data points, you pass them through Astec, get the predictions. Look at the top few predictions. Most of them should be positives. Some of them are going to be negatives. These negatives are the ones where Astec was super confused about. You take those confusing negative labels and that creates a set called as SI hat. Those are your negative training labels. Those are your negative training labels, where Astec predicted that they were positive, but they're actually negative. You take those SI hat and you do a few more epochs over your Astec models so as to train a Z tilde and a W tilde. Remember, you are not touching your Z and W that you trained in your module 3, but you're creating new Z tilde and W tilde. Okay. Now, if you really think about it, module 1's Z and W you threw away. Okay, Z naught and W basically, right? W hat in module 1, right? Module 3 basically has your Z and W that you trained. And re-ranker basically also has its Z tilde and W tilde. You use all of them at inference time. So what happens at inference time? Okay, at inference time, you basically get a data instance. You essentially create a V out of it by doing this embedding layer on top of it. So of course you get a bag of words representation to embedding layer, and then you get a V out of it, and then you look up into your two approximate nearest neighbor search indexes. Of course, you have to keep them in RAM, right? And they get a set of relevant labels, okay, S hat. Now, when you get these set of relevant labels, you also get the similarity scores, small s. You keep those similarity scores. Our final score is going to be computed as a weighted combination of 3 things. Okay, the similarity scores coming from the approximate nearest neighbor search index, the similarity as computed using our module 3's representations, and then finally the similarity as is computed using our re-ranker, using the re-ranker. Okay. So you basically have that these 3 things, they're combined using your betas and alphas as you see them, and betas and alphas, of course, hyperparameters to be tuned by validation data. And then you can actually also have an ensemble of 3 learners as to come up with more robust inferences and predictions. Okay. So how does Astec perform? Now, people compared Astec on 2 different kinds of matrix, precision and PSP, so as to also account for tail and so on. And people compared, Astec on several kinds of algorithms. So this is and several data sets. So this is the query to bit phrase Bing data set. This is public data sets, Amazon titles, and more data sets which are there in the paper. I'm not showing them here. Okay. They were compared. So Astec is just without an ensemble. Astec 3 is an ensemble of 3. These 2 baselines are essentially, MAC and slice are the baselines, which are the low latency short text baselines. So the closest to what Astec does. XML CNN baseline is essentially a deep learning kind of baseline, and attention XML, XML CNN, attention XML are deep learning baselines that you see here. And then Parable, Bonsai, Dismec are all non-deep learning based baselines, either tree-based baselines or one versus all classifier based baselines. Okay. So what do you observe? You observe that Astec is actually 2 to 12 times more accurate and 5 to 13 times faster to train. Okay, so if you look at Astec, it can be 5 to 30 times faster to train, or 2 to 12 times more accurate compared to the baselines, compared to the baselines that you see on public data sets, on these public data sets, Amazon and Wiki titles and so on. Okay. So on the Bing dataset, it is essentially 19% more accurate than the closest baseline. Okay, so that's that. In fact, in real deployments, people found that in suggesting personalized ads, it led to 6.5% higher CTR and 5% more revenue compared to the current Bing production system in 2021. Okay. Query to bid phrase computation, well, it led to 1.6% increase in revenues, 2.9% improvement in match quality, and 8.6% in query coverage. So basically, it has been deployed in Bing production system and seen to perform extremely well. Here are some examples of how Astec's predictions look like. So if you basically give a query, what is diabetes type 2? And you try to find bid phrases, Astec leads to super similar bid phrases, while other algorithms which were deployed in Bing do not lead to very good results. In fact, it leads to some of those bad results. What is email marketing? What is PSTD2? What is anemia? They have to do nothing with diabetes type 2. Okay. Similarly, if you use Astec for finding categories for Wikipedia titles, now Astec comes up with really relevant and diverse titles compared to other baselines, which sometimes lead to extremely incorrect titles. So in summary, in this video, I talked about DeepXML, which is a 4-step pipeline. So it basically in the first module tries to learn intermediate near final feature representation Z0 for various data points. In the meanwhile, it sort of learns this V, which is basically very important and going to be transfer learned in later modules. In module 2, you basically take this V and essentially some representation of those labels and create approximate nearest neighbor search indexes. In module 3, we essentially do hard negative mining and using this approximate nearest neighbor search. You also basically do transfer learning by taking the same V and transferring it for the final task rather than just the surrogate task, right? So surrogate task, of course, was to do label clustering. I mean, training on label clusters rather than actual labels. And then in the module 4, you basically train your delta and your overall, you basically come up with the overall representation Z. So basically you train your delta, which involves R, basically, right? While also training the W, which is the weights of the final layer. Okay. So that's that. So that's basically DeepXML and Astec. We looked at Astec, which was an algorithm based on DeepXML. If you want to play around with the code, that's the code. And that's it for this video. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.